Hi there, my name is Kirsten Carmel, and today I want to share with you a lesson on energy. We will be solving a problem called the frictionless roller coaster. Here's our roller coaster. As you can see, A, B, C, and D represent different peaks and falls on the roller coaster. We are told that the roller coaster's initial velocity is 0 and that there is a height difference of 25 meters between point A and point B. The topics we will be tackling in this presentation are: at which point is the kinetic energy minimum? At which point is the gravitational potential energy maximum? Is the energy at point A greater than, smaller than, or equal to the energy at point D? We will be talking about energy conservations in a closed system. We will find out the roller coaster speed at its lowest point, and we will cover what to do if you are not given the mass. Kinetic energy is the energy that an object possesses while it is in motion. We can define kinetic energy through the equation Ke equals 1/2 mv squared. As a quick note, kinetic energy can never be a negative value. The smallest value of kinetic energy an object can have is 0. This equation tells us that in order to have kinetic energy, an object must be moving. In our illustration, there is only one place where the roller coaster is not moving. This is at the instant right at the beginning of the ride. The point at which the kinetic energy is minimum is point A. Gravitational potential energy in this situation is the energy that the roller coaster possesses due to its height or elevation. We can further define gravitational potential energy with the equation PEG equals mgh. Our question B asks us, at which point is the potential gravitational energy maximum? We know that from the equation for PEG that the position with the greatest height will have the greatest potential energy. We compare the different points on the roller coaster to find which one has the greatest height. From the illustration, we can deduce that this must also be at point A. At this point, you might be wondering, how is it possible that both answers are point A? This is a question about the conservation of energy. With any object in a closed system such as this, there is an exchange that is happening between kinetic and potential energy. The energy is never lost, it is simply converted. This roller coaster is a closed system because there is no energy lost to the environment, friction, or outside forces. But then whenever a physics problem tells you something is frictionless, this probably means that you're working on the closed system. The amount of kinetic and potential energy changes from place to place depending on the circumstances, but it is important to point out that their sum, the total energy, is consistent throughout. Conservation of energy means that all energy is conserved in the system and no energy is lost to the environment. Knowing this will help us answer part C, which compares the total energy of point A and point D. We now know that the total energy of all points of the roller coaster are equal. We can express this mathematically as E total equals EA equals EB equals EC equals ED, where EX, or E of any variable, is equal to kinetic energy plus potential energy. The total energy at point A is equal to the total energy at point B, C, and D. We can use our knowledge of kinetic and potential energy to answer the question E, which asks us, what is the roller coaster's speed at the lowest point? Remember, because this is a closed system, the total energy at the top of the roller coaster is the same as the total energy at the bottom of the roller coaster. At the lowest point of the roller coaster, point B, the potential energy of point A has been converted into kinetic energy. We can describe the total kinetic energy at the beginning of the roller coaster as E total equals PE initial plus KE final. KE initial. We can describe the total energy at the lowest point of the roller coaster as E total equals PE final plus KE final. Remember that E total is the same in both equations. We can set these two equations equal to each other. And now we can make substitutions for the potential and kinetic energy equivalencies. You may have noticed that our initial velocity was 0, which means that our initial kinetic energy is also 0. Notice that we also consider our final height to be 0. This is because we are simply considering the change in height, or delta H. We can now simplify our equation for the system. Notice that we are not given the mass of the roller coaster. This is common in problems with energy considerations. The mass is often not necessary to solve the problem. One must find a way to cancel the mass out algebraically, either through a system of equations or by creating a system as we have below. Here we can cancel mass as it appears on both sides of the equation using algebra. We now isolate the V final and substitute in our known values into the equation and solve. The velocity of the roller coaster at its lowest point is 22.1 meters per second. That concludes my presentation on a frictionless roller coaster. I hope you have found this useful, and thank you for watching.